Hello again, physicists. Today we are talking about something we've already explored a little bit in class. I am talking about friction. Keep in mind, friction is a force. Therefore, friction is something that can be drawn in a free body diagram like I did here and here. Friction will be represented with a vector arrow just like any other force would. It's important to keep in mind that the direction in which friction will act will always try to oppose the intended motion of an object. In other words, what direction is it trying to go in? For example, if I have a red box like right here and I'm giving it an applied force either to move it to the right, whether it be accelerating, moving at a constant velocity, or even if the box is at rest, the intention of this applied force is to move the box in some way to the right. Therefore, friction will oppose that intended motion by acting to the left. Same thing, if I'm on an incline, we know that it is the force of gravity that is going to want the box to slide down the incline. Well, friction will want to counteract that sliding motion down the incline by acting up the incline. Alright, so that's all fine and dandy, but what is really causing friction? Where does friction really come from? Well, if I take this scenario over here where I have my red box on a blue table and I zoomed in by a lot, my apparently smooth surfaces wouldn't really look so smooth. They would actually look something like this, where I have these little peaks and valleys along the surface. And both surfaces have these peaks and valleys, no matter how smooth it may appear. You get down small enough and smooth surfaces will look rough like this. It's the interaction of these little peaks and valleys between the two surfaces that cause friction to occur. So that's what's happening really at a microscopic level when we're talking about friction. In class, we conducted a little investigation to see what variables could potentially contribute to a force due to friction. And we ended up saying that really there were two significant variables: the nature of the material, which we are going to refer to as being the coefficient of friction, as well as the normal force. So as far as an equation goes, if we wanted to actually determine what is the force due to friction acting on an object, we only need to know a couple of things. First off, what is the normal force acting on the object? And then what are the two types of materials that the object and the surface are made up of? Because that will tell us what the coefficient of friction is. This thing right here, this little symbol, is the Greek letter mu. That's the symbol we use for the coefficient of friction. And this is a number that usually is either provided to you, or it's in a table where you can look it up, or it's what you're actually trying to solve for. Mu is a unitless value. This is the first time we have seen a variable that doesn't have units associated with it. The reason why it is unitless is because the coefficient of friction, by definition, is actually the ratio between the frictional force an object experiences and the normal force acting on it. So really, mu by definition is this. And if we do a dimensional analysis on this, you can see, well, the frictional force is measured in newtons. The normal force is measured in newtons, so they cancel each other out. So that's why our coefficient of friction is unitless. And again, this is completely dependent upon the material of the surface and the object. What are they made up of? You know, the coefficient of friction between rubber and ice will be very different than the coefficient of friction between sandpaper and rubber. Next, we're going to discuss two different types of friction called static and kinetic friction. To begin, I'm going to show you a video of a scenario, and then we'll talk about the graph that is to the left of that video. So here's the video. I am pulling on a block. I've added some extra mass to the block to make sure that we're seeing the effects that we should. And at the beginning, when I pull on the block, it's not actually moving, but then it starts to move and I drag it onward at a constant velocity. So let's play it one more time just so that we can see what's happening. So I'm pulling, and then it starts to move at a constant velocity. All right, so that's what's happening in reality. Let's talk about what the graph is telling us. So at the beginning, for the first couple seconds, I am pulling right there. I am pulling. It may not look like it, but I am. The reason you really can't tell is because I'm not pulling with enough force to actually make the object accelerate and then start moving. So the object is staying at rest right now. And if I wanted to draw a free body diagram when the object is at rest, well, we can say that we have our gravitational force pulling down on it, the normal force of the table pushing up on it. I am pulling with an applied force to the right, and I have friction. I have friction acting on this block. In fact, it is the friction that is preventing the block from beginning to accelerate, because with whatever applied force I pull with, the frictional force is matching that applied force and therefore keeping the block from accelerating and therefore begin moving. On this graph over here, the region of the graph that is on the left-hand side of the dotted line represents the time at which the block is at rest. And this is a plot of my applied force versus time. Now, if I go a little further in my movie, boom, I begin to move, and now I'm moving specifically at a constant velocity. So if I wanted to draw a free body diagram now, when I'm moving at a constant velocity, truth be told, it's not going to look a whole lot different. I'm still going to have the same four forces acting on the object. And the frictional force will still be equal to the applied force. However, if we look at the graph that goes along with this scenario, we can see that when we're moving at a constant velocity, our frictional force dramatically dropped off once the object began moving. What this is telling us is that friction doesn't behave the same when an object is at rest versus an object that is moving. And that means there are actually two types of friction: static and kinetic friction. Static friction is the friction that keeps an object at rest, whereas kinetic friction is the friction that is trying to impede the motion of an object as it moves at a constant velocity, or even accelerating. And you can see that the static friction at its peak is significantly higher than the kinetic friction. And that'll always be true. Static friction will always actually be a larger force than kinetic friction. Lastly, I want to explain substitutions that can be made related to this equation for the force of friction, because based on free body diagrams, there are several substitutions that we can oftentimes make. So I have a particular object on a surface. We are pulling on it with an applied force, and we have friction acting on the object as well. There's my applied force, there's my friction. We could determine that the frictional force is the coefficient of friction times the normal force acting on the block. However, if we can say that the acceleration in the y direction is 0 meters per second, that means that the frictional force and the gravitational force are balancing one another out. In other words, they are equal in magnitude. And that means that I can then make a substitution for the gravitational force. It will take the place of the normal force due to this fact. And that's what I noted over here. We can then go a step further than that. We can say, well, we know that the gravitational force is really the mass of the object times the acceleration due to gravity. And I can take this and I can plug it in for the gravitational force over here. So ultimately, I can say that the force of friction in this particular case is equal to the coefficient of friction times the mass of the object times the acceleration due to gravity. The only reason I can make those substitutions here is again because we are saying that the object is not accelerating in the y direction. Therefore, these two forces in my free body diagram are equal to one another in terms of their magnitude. That's all I have related to friction. Make sure that you copy down the details here and be ready to ask questions come Monday. Until next time, physicists, until next time.